Okay, this is an introductory right angle relative motion problem. You can pause it if you want to copy out the question here. A river runs west at 3 meters per second. A man swims north at 5 meters per second with respect to the water. So the WRT there means with respect to the water. The river's 12 meters wide. Where does he end up? So here's the question. We have a river, and from one bank to the other, it is 12 meters across. There's a man in the river, and he can swim with respect to the water at a rate of 5 meters per second. However, while he's doing this, the water of the river is moving this way at 3 meters per second. So the man is moving this way at 5, in water that's moving this way at 3. So his motion going across is going to look like this. He's swimming directly north in the water, but as the water moves west, this is what his motion looks like. If we were to take the water out, he's still swimming, but take the water out of our view, and just look at the man with respect to the ground, you're going to see motion like this. He appears to be moving on this diagonal, which is both north and west at the same time. We're going to calculate exactly what that velocity is by adding our vectors. It's actually not required to solve this particular problem, but I'm going to show you how to do that as well. So the river is running west at 3 meters per second. So the velocity of the water with respect to the ground is 3 meters per second west. The man swims north at 5 meters per second. So the velocity of the man with respect to the water is 5 meters per second north. So the velocity of the man with respect to the ground, as he swims in the water and the water moves, the velocity of the man with respect to the ground is going to be equal to the velocity of the man with respect to the water plus the velocity of the water with respect to the ground. So this is as the man swims in the water, and this is as the water moves with respect to the ground, or the run of the river. These are vectors that we're adding, so we're going to draw a triangle. We have a vector that is 5 meters per second north. That's the man in the water. We have a vector that is 3 meters per second west. That's the water with respect to the ground. So the man with respect to the ground is going to be the resultant vector. We put these two tip to tail, and then starting at the tail and moving to the tip, this is the velocity of the man with respect to the ground. So we're going to need to find this angle and this magnitude. The magnitude of the velocity of the man with respect to the ground is the square root of 3 squared plus 5 squared, because a squared plus b squared equals c squared. So c is the square root of a squared plus b squared. This is just the Pythagorean theorem. You can review the Pythagorean theorem if this part's not dead clear. So the velocity of the man with respect to the ground's magnitude is the square root of 9 plus 25, that's 34. And the square root of 34 is 5.8. So the velocity of the man with respect to the ground's magnitude is 5.8 meters per second. And it's kind of northwest, but it's not exactly northwest because the magnitude of the north component is greater than the magnitude of the west component. So we need to do a little bit of trigonometry here. These two lines here mean magnitude. An arrow over top of our variable indicates that it's a vector. A vector is a quantity that has a magnitude, that is how big it is, and a direction, which way it's going. We put two lines here to indicate that in our math, we're only interested in the magnitude. Okay, so to find our direction, well, this is a right angle because north and west are right angles from each other. That's a right angle. The tan of this angle is opposite over adjacent. So I can write the tan of my angle is opposite over adjacent. So my angle is arctan of the opposite over the adjacent. So my angle is, I'll take 3 divided by 5. Gives me 0.6, and then the inverse tan is 30.96. Or I'm going to call that 31. It seems close enough. Okay, so to find this angle, I looked at my right angle triangle and I found opposite divided by hypotenuse. Opposite divided by adjacent. The tan of that angle is opposite over adjacent. So the inverse of the tan function, we actually call it arctan because it's not strictly speaking an inverse, but that is the arctan of 3 over 5, and for my calculator that's 30.96, so I'm going to go with 31 degrees. So what that means is the velocity of the man with respect to the ground is 5.8 meters per second north, 31 degrees west. Now, if we found this angle instead of that one, we'd be correct in finding this angle, but we'd have to interpret it correctly. This angle would tell us how far we've rotated north of west, whereas this angle tells us how far we rotate west of north. And that's the way we typically indicate these directions. So if you find yourself having done your analysis, you found your angle here, just be aware that if this was your angle, you'd report it as west, and then that angle would be 59 degrees north. And then switch them, put north first, and find the complementary angle or supplementary angle, whichever that's called. I always forget which one. Okay, so now to answer our questions. So that was the resulting velocity. Where does he end up? Well, as it turns out, we didn't actually need to find that resultant vector. I just wanted to show my physics students how to do that. That's why I threw that in here. The man is swimming north at a rate of 3 meters per second. And as he does so, I'll show you the river again. The question said that this distance from here to here is 12 meters. And our man is swimming this way at 5 meters per second. Now, that distance that he swims directly across is 12 meters, whether the water is staying still or moving. See, if the water's moving, his motion ends up on this angle, but he's still just going with respect to the water 12 meters. And he's swimming at a rate of 12 meters per second. Sorry, of 5 meters per second. So I can write it out like this. The time, delta t, the amount of time that it takes for him to swim across the river, is going to be equal to the displacement, and that's his displacement in the y direction. So I'm going to call north-south the y direction and east-west the x direction. His displacement in the y direction divided by his velocity in the y direction. Now his velocity in the y direction is just his 5 meters per second north. So the amount of time that he takes to cross the river is going to be 12 meters divided by 5 meters per second, which is 2.4. So this takes 2.4 seconds. Okay, so where did the man go here? Here we go. So 2.4 seconds after he started swimming, he's made his way across. How far up the river did he end up? Well, for that, we have to look at his horizontal component of his velocity. See, what we're interested in now is what was the man's displacement in the x direction? Well, that's going to be equal to his velocity in the x direction times the amount of time that took. His velocity in the x direction was based entirely on the velocity of the water. You see, as he's making his way across, he's swimming north and the water's moving west. His westward motion depends entirely on the motion of the water. So the x component of his velocity is simply the 3 meters per second west that the water is doing. We multiply that by the amount of time it took him to cross the river, which was 2.4 seconds. And that's going to give us 6 plus 1.2, 7.2 meters. So the way we interpret that physically is as the man swims across at 5 and the river moves at a rate of 3, he ends up a distance of 7.2 meters west up the riverbank.